Okay, so today we'll start talking about trusses and how we do the matrix and putting that together for doing our analysis on it. So background, we can determine deflection with PL over AE, and we know our spring equation is deflection times our spring constant equals our force, right? So if we do some substituting, then we can say that our spring constant is AE over L, right? Or our stiffness, if you will. So then we can do deflection and a force. So we'll apply that when we're working through this. So remember our one-dimensional spring and what that looks like in matrix form, right? And we'll work through, and at the end we're going to do an example that we'll put all this together. So when we have a truss element, right, this is our standard form, right, this is X and Y at one node, X and Y at the other node. So these two are node 1, these two are node 2, right? And see how our K's are the same as they were for our standard, our simple one-dimensional spring, right? So our X and Y for node 1, X and Y for node 2, and then our forces in those directions on that, right? Because we're doing K times U1, 0, K times U2, 0. These are all going to be zeros, right? For one end versus the other end. Okay, and this generalized matrix is for one where it's your axis aligned, so the truss is horizontal or it's vertical. All right. Well, yeah, it's horizontal or vertical. If it's not, oh well, we'll talk about that in a second. So the local is aligned with the truss, and our global is going to be our big XYZ for the frame of our whole structure. And so when we get to the angled one, right, because we have to define, we've got to go some distance in the X, some distance in the Y to determine any kind of motion when we have our truss element at an angle, right? So we're going to be doing X or cosine and sine, and so that's why we end up with this generalized coordinate, right? And then I don't think, did I put it in here? Oh, okay. So and then there's the other one that I don't have in there that we'll go through when we do our example problem. But this is what we'll set up, and we'll expand to do a matrix solution on a simple 3-member truss. So before we get to that, just a quick comment on when you're setting up your nodes and your elements, you want to try to be sequential about them. And the reason for that is so that when you set up the equations, that you get most of the values along the diagonal as they demonstrate in the book. I don't have a slide for it. Where'd it go? There we go. Right, that isn't showing it. So our figures, 3.7, 3.8, are providing examples of why you're trying to set your elements and your nodes up sort of in a sequential manner, left to right, top to bottom sort of idea, so that your I don't know, the newer software might not have as big an issue with that. It might reorganize things and set it up properly. I don't know. I don't know enough about the software side. But to simplify the calculations and make it easier for the computer to compile through the information, then if we set it up so that, you know, we're doing things in an orderly fashion and moving kind of in one direction and not making this node 1 and this one node 2 and this one node 3 and this one 4 and that 5 and that 6 and that 7, that kind of deal. As long as you're not doing that, then it should move through the stuff pretty quickly and not creating hassles, and certainly makes it easier when you're trying to do them by hand, because it'll drop out a lot of the equations. So, and you can also, whenever you have objects that are symmetrical, especially if they're large and complicated, then you can take advantage of symmetry to minimize the number of calculations that have to be done and simplify your model. But you do need to, you know, constrain the line of symmetry appropriately so that it matches what would actually be happening if you had put the whole part together or had the whole device there, right? So you have to put half the load at node 4. You know, you don't want this going, this can go up and down, but you're going to constrain it in the X, and you'll constrain that one in both axes. Okay? So just a quick comment on that. But I want to go through expanding our truss, right? So they have a picture in the book, an example. Let's see. So figure 3.2, right? Move this over so it's okay. So we have our nodes labeled 1, 2, 3, elements K1, K2, K3, or, well, they're not Ks, but I put the Ks on there to associate it with what we're doing, right? So if we, and this takes a long time to write out, so I will post this, and I'm not going to write it out because we'd be here a whole hour watching me write, or 2 hours watching me write. I'm sure you don't want to do that. Okay, so we started out, we know we have our generalized form. Where's my pointer? So let's see. So we're starting out with our generalized form, and let's see. This is where we really need. See if I can get this. Okay, so we're on element 1, and let's scroll this. Okay, good, that'll work. Okay, so we're on element 1, and we're setting up our matrix, and we're on node 2, right? So this is our element. For this particular element, node 2, we don't have any X translation. So all of these are going to be 0. 0 for the U, 0 for the V, right? Then when we get down to this Y direction, we can have some translation for V2 and V3. Then if we go up to node 3, again in the X we got all zeros, and for the Y we can have some translations for V and. Does that make sense? You guys following that? How we put that together and what's going on? So we can do that, and then it says that, well, because we have what, 3 nodes, or excuse me, 3 elements, and we have 2 nodes at each element, so we're going to end up with a 6x6 matrix. So if I write that out, or if I take that and create a 6x6 with all the values, so for element 1, or for node 1, node 2, node 3, okay, so we just duplicated that for all those. Does that make sense? You guys can follow what's happening there. So now if we expand that to node 2, see which, this is node 2. So node 2, excuse me, not node 2, element 2, right? For element 2, well, that's a little better, right? Well, it's off the page, but they define, so somebody went through and did all the transformations and did the matrix and defined this for us for any element that's at an angle, and we just need to know what the angle is, and we're dealing with our global coordinate system, right? So we're here, we can be here at element 1. This will be our X, our Y, and we're going to have to go 135 degrees to get to this angle, because these are similar lengths. This is 45, so that means this is 135. Okay, so if we take the cosine of 135 and square it, and then the cosine of 135 times the sine of 135, and carry on through all that, we'll develop, I'm doing this in the right order, okay, we'll get, so here's, so element 2, or yeah, element 2 all ends up being, 0.5s, and it's a full matrix, and then when you expand it out to the 6x6, so these are going to U, this is going to B2, so 1 and 3 are the nodes that 1 and 3 are the nodes that element 2 is in contact with, right? So we can expand it out to 6, the 6x6. Then if we do element 3, right? So element 3, element 3 go. Again, we're horizontal, we're in line. This is, so node 1, node 2, set up our matrix, expand it out to 6x6, and then we can add them all together. And we'll end up with whenever it decides to appear. I wrote it with magic, or with invisible ink, and when you put on the light, it magically appeared. Anyway, we can get, that makes it worse. There we go. Okay, does that show up better? So this would be our completed matrix. And it's washing out again. Okay, so, and we just add them together, so I had a couple units there, most of the others are all singular. There's a K1 and a K2 here, right? So that's what it would look like, and you would begin to solve. So what's the first thing we do when we get to this point and we have our structure, our matrix all set up? We're going to start considering the load or the boundary conditions, right? So we can start canceling stuff out and reducing. So we know that we have no displacements at U2, B2, and U3. So those all go to 0.